Good morning, afternoon, evening, or night, depending on your time zone. And thanks for joining this presentation about multiphoton absorption excited upconversion luminescence in multimode optical fibers. This is a work made as a collaboration between the University of Rome, University of Brescia, and University of Limoges. One of the advantages of multimode fibers is that they can carry light beam with very high peak powers without occurring in permanent damages. This allows to work in a regime where new nonlinear effect can be observed. In particular, recently we reported the presence of nonlinear losses ascribable to multiphoton absorption mechanism, analyzing their effect on Raman-Soliton propagation in graded index fibers. Nonlinear losses introduce a fundamental limitation to the energy transmission capabilities of optical fibers and would affect the power scaling of spatiotemporal mode locking in multimode fiber lasers. To date, a microscopic interpretation of this intriguing phenomenon is still missing, and here we fill this gap of knowledge by linking the multiphoton absorption in commercial optical fibers in the infrared spectral range with the presence of visible photoluminescence due to defects and impurities that is dubbed upconversion luminescence. In this presentation, I will first introduce some experimental observation by showing our samples, the experimental evidence of nonlinear losses and multiphoton absorption, as well as the spectral characterization of the upconversion luminescence. Then I'll move to the modeling part, where we estimate the average number of simultaneously absorbed photons, and then by numerical simulation we further confirm it by underlying the role of the temporal dynamics. And upconversion luminescence is a phenomenon that can occur in general in several kinds of fibers, but for sake of simplicity, in this presentation I will focus on the graded index fiber with 50 micron core diameter, and only in the conclusion I will make a comparison with the step index fiber. The index grading of our sample is given by a germanium doping. Here I show an SEM image of the section of our fiber and the measured parabolic shape of the germanium concentration. As I said before, upconversion luminescence is due to defects and impurities, so it's worth saying since the beginning which are the main defects contributing to luminescence. In case of germanium doped silica, the main contribution is given by oxygen deficiency centers, that is nothing more than a missing oxygen atom between two atoms of germanium or silicon, and this produces a violet-blue emission at 400 and 460 nanometers. On the other hand, in the case of undoped silica, the main defect contributing to luminescence is the so-called non-bridging oxygen hole center that produces a red emission at about 650 nanometers. The first result that I'd like to show is obtained with an input wavelength of 1030 nanometers and a beam diameter of about 7.5 micron and a repetition rate of 100 kilohertz. We observed a drop of the transmission when the input peak power is higher than 1 megawatt for fiber length smaller than 10 centimeters. Now we wonder, is this attenuation due to multiphoton absorption? The answer is given us by the simultaneous appearance of the upconversion luminescence that appear in a green fiber as an array of emitting spots. The light is in fact periodically side-scattered at points of peak intensity generated by the spatial self-imaging. What we would like to do at this point is to study the spectral features of the upconversion luminescence. In order to do that, we collect the light side-scattered by means of an imaging lens, and we send it to a microscope, producing the image that I just showed before, or a spectrometer. Here I plot the spectra collected in the log scale for several values of the input peak power. The spectra contains many information. First of all, we can observe the nonlinear broadening of the pump. Then also the presence of a contribution of the third harmonic generation at about 345 nanometers. And of course, the most relevant feature is given by the contribution of the germanium oxygen deficiency centers and the non-bridging oxygen hole centers defect that produce this luminescence at 400 nanometers and 650 nanometers respectively. I can now present a very simple model to describe our observations. As first approximation, we can consider the upconversion luminescence being excited by a single N-photon absorption process. A scheme of the physical mechanism is shown on the right. So N pump photons are simultaneously absorbed, promoting an electron from the ground state to an excited state. This non-radiatively decay into an intermediate level and eventually goes back to the ground state by emitting a luminescence photons. This scheme is resumed by the formula on the left, where the intensity of the upconversion luminescence is proportional to the nth power of the input peak power. And N represents an effective number of absorbed photons, including all the possible contributions that are not explicitly taken into account. Now, if I plot here the intensity of the upconversion luminescence as obtained as the integral of the experimental spectra as function of the peak power in the log-log scale, we see that both the violet and the red contribution have a linear trend, and also with the same value of the slope n. This is due to the fact that oxygen deficiency centers and non-bridging oxygen hole centers absorption bands are almost overlapped. In particular, we get n equal to 5, that is coherent with the prediction, since the absorption band peak of both is around 250 nanometers. We can further stress our model by changing the number of absorbed photons. In order to do that, we vary the wavelength between 650 and 940 nanometers. Here I report the spectra, and as you can see, the peak at 650 nanometers related to the non-bridging oxygen hole centers emission is partially covered by the source. For this reason, I only refer to the germanium oxygen deficiency centers luminescence. Again, I plot the integral of the spectrum of the upconversion luminescence as function of the peak power in the log-log scale. And we see that still we have some linear trend with values of the slopes n that are smaller than the previous case at lambda equal to 1030. This confirms our prediction. In particular, what we obtain is a value of n equal to 3, close to n equal to 3. That is the theoretical value expected for lambda equal to 750 nanometers in order to match with the germanium oxygen deficiency centers absorption band. We also performed some numerical simulations that allowed us to confirm the validity of our model, but also to explain another phenomenon that we observed. In particular, this is the slow modulation of the upconversion luminescence fluence along the propagation. As you can see on the figure on the right, the fluence has a maximum at about 3 millimeters. The upconversion luminescence fluence obtained by 5-photon absorption is proportional by definition to the fifth power of the intensity of the light beam inside the fiber, the effective area of the beam, and the pulse width. Remarkably, our results are well reproduced by simulation using a 3D+1 generalized nonlinear Schrödinger equation, where you can see we have exactly the same shape of the fluence with a maximum at the experimental values of 3 millimeters. When we consider the fifth power, exactly the fifth power of the intensity according to the formula on the top. Moreover, we can state that this low modulation is due to the temporal dynamics. In fact, as shown in the inset, the pulse width delta t increases with the fiber length, while the effective area oscillates with a constant amplitude. This being defined as a time-independent quantity. In fact, in its definition on the bottom, the electric field is integrated on time. As a last result, I present a comparison between step index and graded index fibers. As the picture on the right shows, there are several differences between these two cases. First of all, due to the lack of the index grading in step index fiber, we have only one emitting spot due to the Kerr effect without the self, since the self imaging is missing. Moreover, we can see that this emitting point is much more red colored than the ones in the green case. And this is due to the fact that since the doping is absent, the non-bridging oxygen-hole centers luminescence is more intense than the germanium oxygen deficiency centers. But still, we can observe some peaks in the range between 400 and 450 nanometer, even in the step index fiber. And these are due to germanium impurities or silicon oxygen deficiency centers. I also would like to underline that I normalize the two spectra of green and step index to the same value at 650 nanometer in order to underline another interesting aspect. We see that in order to have the same amount of red light, we need to saturate the spectrometer in the case of the step index fiber. This being to the spatial self-imaging. In fact, the light scattered out by defect is much larger in graded index fibers than in step index fibers, and this can be seen also in terms of transmission. In fact, nonlinear losses are more important in green fibers than in step index fiber. Here, I present the attenuation as function of the input power, and we can see that when the attenuation is important in green fiber, is still negligible in the case of the step index. So to conclude, we have shown that multimode optical fibers undergo multiphoton absorption when operating close to the damage point. Absorbed infrared photons lead to visible upconversion luminescence, forming an array of blue points for germanium doped graded index fiber. And we estimate the number of absorbed photons being n equal to 5 at 1030 nanometers by distinguishing the role played by non-bridging oxygen hole centers and oxygen deficiency centers. Experimental results are validated by numerical simulation and will show the role played by the temporal dynamics of the laser beam inside a fiber. And then, as last, we compare graded index and step index fibers, further confirming the role played by the multiphoton absorption excited upconversion luminescence on the nonlinear losses. In terms of perspectives, our results will be of importance for the fundamental understanding of extreme nonlinear phenomenon, as well as for technological applications. I would like to cite the high-power fiber lasers, nonlinear multiphoton microscopy and endoscopy, laser ablation, and micromachining. Moreover, multiphoton absorption excited upconversion luminescence would be a tool to directly monitor the presence of nonlinear losses, and also provides a new mean to extend the fiber supercontinuum bandwidth into the ultraviolet range. With this, I conclude. Feel free to contact me if you have some questions to my email address, and if you wish to have some further details, you can also check on this paper that we have that has just been published, in which several of the results that I presented today are reported. Well, that's it. Thank you for your attention.